Thanks for the introduction. Yes, so I'm Felix from Tilburg University, and I'm going to talk about bounding option prices using tools from polynomial optimization. And as has been said, this is the outcome of my secondment at CNRS LAS in Toulouse at the beginning of this year. And we collaborated with quite a big group of people. So it was Didier Henrion, me, my supervisor Etienne de Klerk, and then Milan Corda, Jean-Bernard Lasserre, and Victor Magran also joined the team. So let's have a look at the agenda. Oh, sorry. Good. I'm going to introduce the concept of options as a financial product, and then we're going to formulate mathematically the problem of pricing these things. And then afterwards, we're going to look at something called Autorange and inner range, and these two concepts will make sense as soon as we get there, I hope. So beginning this talk, I would like to tell you what an option is. And in simple terms, it's a derivative security. And now there might be the question, what is that? So a security is simply a tradable financial asset. And the word derivative here implies that it derives its value from another asset, which we call the underlying. Now, this means an option is a tradable financial asset whose value depends on another asset like a stock, a currency, or a commodity. But this is still a bit vague, so let's look at a more precise definition or an example, if you will. So in this talk, we will mainly be interested in European call options. And these are contracts that give the owner the right, but no obligation to buy an underlying asset at a fixed price at a predetermined date in the future. And this fixed price will be referred to as the strike or strike price, and the date in the future will be called maturity. But if you were never in touch with options, this might still be a bit abstract, so I'm going to give a really hands-on example in a minute, but I forgot to say, if there are any questions, please feel free to interrupt me and I will try to answer them as good as I can. So back to European call options, consider the following situation. We have two parties in a market, which we call Alice and Bob. And now let S be the stock of a company and S sub T be its price at time T. And now Alice sells Bob a European call option on that stock S, and the strike will be denoted by K and the maturity by T. Now time passes and maturity comes, and then Bob will have two options basically. So he can exercise the option, which he will if the option, if the stock price at maturity is greater than K. And exercising the option simply means that Alice has to sell Bob the stock S of that company for the predetermined price K. Now, if at that time in the future, the stock price is lower than K, then Bob will not exercise the option because it would be cheaper for him to buy that stock at the stock market, right? So in this situation, we can look at Bob's payoff function, which looks like this. Whenever the stock price, which is denoted on the x-axis here, whenever the stock price is lower than K, it makes no sense for Bob to actually exercise the option. So there will be, since it's the option part is that he can choose to exercise it or not. And so if he doesn't exercise it, there is no payoff. The payoff is zero. But as soon as the stock price is greater than K, what Bob can do is buy the stock from Alice for K and immediately sell it at the stock market for the current option price. So the resulting payoff will be exactly the difference between the stock price at maturity and the predetermined strike price. And what we can see nicely here is that the payoff function of this financial product is non-negative. And this implies that the option itself must have some non-negative value. And we will today try to answer that question, how much should Alice charge Bob for this option? So in other words, what is an option worth? And there are two main approaches in the literature that use semi-definite programming. And the first one is that you can simply assume that the price of the underlying asset follows a stochastic differential equation. But the drawback here would be that this model is highly susceptible to model misspecifications and parameter estimation errors. And we will follow another approach in this talk, and it is the second one here, where we solely assume the absence of arbitrage opportunities. Arbitrage, in this case, simply means that you cannot make money deterministically without risk. So an example for arbitrage would be a sequence of trades where in the end you have more money than you started with without having to pay for this with the risk of losing money. Yes, so the nice thing about the second one here is that it can be shown that this is in fact equivalent to the existence of a probability measure under which the option prices become martingales. And this is something we will use in the mathematical formulation for this. Either approach can lead to an optimization problem that can be approximated using semi-definite programming techniques. In practice, you can also use different approaches where you use numerical methods and all these Monte Carlo things and so on. But well, since we're interested in polynomial optimization, we're going to follow this way here. Now, the question would be what to aim for, because in general there is no exact option price. So it's not like there's one exact price that can be determined, but rather a range of prices. And this range basically means that every price within that range would be consistent with the market and the other options traded therein in terms of the no arbitrage assumption. For example, to avoid this arbitrage assumption, we would have to have that if we have an option with a lower strike price on an asset, that this one has to be more expensive. So consider the line down here. If we have two options on the same asset with different strike prices, then we have here the payoff functions. And now you see that if K1 is smaller than K2, then obviously this payoff function is greater than the payoff function of the other option price with the strike K2. And if that is the case, then, or if the payoff is greater, then of course the option has to be more expensive, right? So yes, this is one example for consistency. And the idea will be that we use observable information to get useful bounds for our problem. And this information may come as moment data, so we can have something like information of how certain assets in the market are correlated. Or we can use observable option prices on the same or correlated asset. Good. So let it be said that, that there are multiple types of options. So it's not that we have these single asset European call options. There are very many. Just to name two more as an example would be here a call on max, where you just take n different assets, and then at the end you choose the most expensive one, and you can buy the one that performed best within that group for the predetermined price K. Or another thing which is called a basket option, where you use this weighted average of a bunch of options. And if that one after or at maturity is greater than K, then you would make the profit of the difference, where the weights are of course positive. This would be something like an index option. So if you use some stock index, then this weighted average would be, or the value of that index at some time t. Now another question would be who actually needs options, and these are well, very important products in the world of finance, and also, for example, for planning security and supply chain processes, then for portfolio hedging, and also for private investors now. So all these Robinhood apps and scalable capital and so on, you can actually now, as a private investor, buy call options on any stock that you want with just a few clicks. So it's also something for private investors. So another word on consistency. Say we have data pairs where these are always these tuples, and the second element will be a real number. The first element will be a function, and we have m of them. And let this phi be the payoff function of an option, which may depend on n different assets. We only consider the non-negative authent here because the implicit assumption is that stocks or the values of commodities or similar cannot be non-negative, cannot be negative. So stock price will always have some positive value or zero, basically. So if for probability measure mu, we have that all these equations here are satisfied for our data pairs, then a consistent price for our option with that payoff function phi is given by this integral right here. And now the question we will try to answer is what's the largest and what's the smallest consistent price for our option? And our option will be the one with the payoff function phi. And this, so what's the largest and the smallest consistent price for our option? So consistent meaning that it has to meet all these equality constraints of the data that is available to us or that we want to use to get a price for our option. Now we're far enough to formulate the problem mathematically. We consider n assets, which we denote by S1 to Sn, and their prices will be given by x1 to xn. And for our problem, we will assume that for every asset there are ni, or asset Si, there are capital Ni options observable with strike prices Kij and prices Qij, and we also assume that some moment information is given. So this might be just a monomial or polynomial, this f here, and then the PL is a real number. Further, we will assume that the dth order moments under a risk-neutral pricing measure are finite, where D is just 1 plus the largest degree that appears in all our data functions. And we just formulate this in one inequality constraint. So for such a measure mu, we want that the 2 norm to the power of D integrated with respect to mu is smaller than some constant m. Fair enough. Now the optimization problem looks like this. So we want to find the lowest and the highest price for that is consistent for our option. So we will compute the supremum and the infimum over all measures mu that are probability measures and that meet our data criteria. So it has to be consistent, and also we want that the dth order moments are finite. Now this here is a generalized moment problem, and these are NP hard in general, but we have some more difficulties here, namely that the support of the measure mu, namely Rn plus, is not compact. And another problem is, at least at first glance, that some of the involved functions are only piecewise polynomials. So if I go back to the last slide, we see that these here are 0 for every x that is smaller than Kij. And so after that, they're just linear functions. So we can just work around that problem really easily by decomposing the non-negative authent here into subsets that are disjoint and partition Rn completely. And we just choose that decomposition in a way that all the functions that appear in our problem are polynomials for every I, basically. So for every component here, we want that all the functions are polynomials on that. But the former, so the non-compactness, is indeed a difficulty. So let's have a look why that is. First, we have here now the Autorange. And for this, I will have to introduce the moment SOS hierarchy, which is due to Lasserre. Quickly, I think most of the people watching have already seen that, but I will nevertheless introduce it now quickly. So let Y be an infinite real sequence, and let Ly be the Riesz linear functional, which maps polynomials to the reals by sending the respective monomial to the corresponding element of the sequence, which is indexed by n to the n. So what this means is basically that if Y is the moment sequence of some measure mu that is supported on a set K, then the operator Ly coincides with the integration operator on polynomials with respect to mu, of course, meaning that a polynomial is simply sent to the value of its integral over K with respect to mu. For a finite sequence Y, we associate to the sequence the so-called truncated moment matrix MRY, which is defined like this. So the entry corresponding to the index alpha and beta is simply Y of alpha plus beta for alpha, beta in n to the n sub r. So these are all the n tuples whose components come to less than r. Such a matrix has dimension SR, where SR is n plus r choose r. And now for Y as above, we can also, for any polynomial G of degree D, define the localizing matrix, which is defined as follows. So the entry at index alpha beta is simply the sum depicted here, where G gamma is simply the these are the coefficients of G. Okay, so now we're almost done with the moment SOS hierarchy introduction. So let K now be a basic semi-algebraic set where we have which is defined by polynomials Hi. And now we consider the following generalized moment problem, where we call the optimal value if we minimize rho minus and if we maximize rho plus. What we do is we simply extremise this integral of f0, and we have some equality constraints and some inequality constraints that have to be fulfilled. Now, if we apply the moment SOS hierarchy, we define R min to be the largest degree that appears in any of the polynomials of our data set. And now for any R that is larger than this R min, the level R moment SOS or the level R moment relaxation of the GMP is defined as follows. We call that rho R minus or rho R plus as the infimum or maximum of Ly of f0, where we have, of course, still our equality constraints fulfilled, our inequality constraints fulfilled, and now we have to have that the moment matrix or the truncated moment matrix has to be positive semi-definite, and the localizing matrices all have to be positive semi-definite as well. Good. So far, so good. The nice thing is that by this hierarchy, we get, if we increase the level, we get tighter and tighter outer approximations of the Konov measures. So basically, increasing R, we get increasing or non-decreasing values for the lower bound, and well, likewise for the upper bound. And this is why we call this the Autorange. And if K is compact, so if the underlying set is compact, this is known to converge. However, we are in the spot that K is not compact because we consider the non-negative orthant. So we basically cannot be sure that this hierarchy will actually converge to the true range that we're interested in. And now the question is, can we somehow compactify the problem to ensure convergence? And for this, we will say the following lemma. If the problem is feasible that we consider, then the infimum, respectively the supremum, is attained. We will not prove this. If you're interested in the proof, it's written down in the preprint, which is available at archive. I will give you a link to that later. And we want to remark the following, that this constraint here is actually the one that ensures the that the optimal solution is attained. So if we do not assume that the dth order moments are finite, there are problems where the support of the optimal solution actually wanders off to infinity. But as soon as you enforce this constraint, we know that there is an optimal solution, for which the optimal value is attained. Good. So equipped with this knowledge, we know that there exists an optimal solution. So say we can find a bound B, depending on the problem data, of course, such that there exists an optimal solution whose support is contained in this box, 0b to the power of n. Well, what we can do then is just replace the non-negative orthant, this non-compact set, which we want to get rid of, by this nice compact set here, and then just apply the moment SOS hierarchy to our problem, and then we know it converges because we have simplified the problem to a compact one. The problem now is that except in special cases, there's little hope that we can actually find a closed form solution for such a bound B. But for example, in the univariate case, it is quite easy to find one, and for any B that is greater than this expression here on the right-hand side, we know that the optimal solution of the problem will lie in an interval 0b, right, for every B that is greater than this one. Okay, so maybe let's have a look at an example. We consider the following problem. So we have one asset whose price is denoted by X, and we have n options on that asset given, or we can observe n options with strike prices Ki and prices Ai. And now we again are looking for a probability measure that has finite second moments, meets all these criteria, and then we're looking for the maximum value of this integral and the minimal value of this integral. Now let M be the index such that Km is smaller than K, so K is the strike price of the option we're interested in. And what we now do is we decompose the underlying set, because we know, especially in the univariate case, we have a closed form solution for that B. So we know the optimal solution will be within that interval 0b here. And now we still have the problem that the functions we're considering are only piecewise polynomials. And now what we do is we simply divide that interval 0b up into segments, so closed intervals here. We slice that up at every k that we encountered, and now we define a new measure mu I for every of these intervals, such that the support of that measure is exactly that interval. And now we can formulate an optimization problem that is equivalent to the one we had before. So it looks like this. And here we simply, we only consider the linear parts of the max functions and just ignore the ones where the corresponding function would be equal to 0. right? And now this is something where we can very simply, apply the moment SOS hierarchy to. And this is what we do. So basically, we introduce a linear operator for every measure mu that just appeared. And now we get something like this. We have still our equality constraints. We have this inequality constraint and the probability measure constraint. And now we have these semi-definite constraints for the moment matrices of the respective measures, and the localizing matrices have to be positive semi-definite as well. And this is now something that we can very easily feed into a computer and just enter optimize and get a nice solution. And this is what we're going to do next. So take, for example, these numbers here. So these are actual prices of European call options on the Microsoft stock from, well, let's say back in the days. And we have 5 different options given, or we can observe, say we can observe 5 different options with these strike prices here and these actual prices. And now say we want to find the range of option prices for an option on that stock with strike price $105. Then solving this analytically, we can verify that the optimal range is, well, the upper bound is 5.125, the lower bound is 3.875, and solving the problem with our by solving with our semi-definite relaxation hierarchy, we find that the hierarchy is exact at the very first level. Okay, this was everything I wanted to say about the outer range. Now we're going to talk about the inner range. Let's see. We will now consider another relaxation hierarchy, which is also due to Lasserre, which does not assume that the underlying set is compact. So we will not need the assumption that we have a compact underlying set, and also we can now throw out the assumption that the dth order moments are finite, which is nice. For this, we first fix a reference measure, which we call mu on Rn. And the important thing about this reference measure is that the measure of the set that we consider, so Rn plus, has to be finite. And for example, we can take a measure like this one here. So we have just a weight function that ensures as x goes to infinity, or the norm of x goes to infinity, well, that the integral of the measure of the non-negative ortho remains finite. The important thing is that we need the moments of that measure to be either be available in closed form or to be efficiently computable. And now the basic idea is to approximate an optimal solution to the generalized moment problem, which we call mu star, with a sum of squared density function. And the question will be, can we find an SOS density function such that the optimal solution d mu star here is equal to hrx times d mu x. This will be the approach that we will take. Well, let's see at the corresponding optimization problem. The level R relaxation of the problem 1, or so the problem that I introduced in the beginning can now be formulated as follows. We still minimize or maximize the integral. I simply wrote only the minimum here now, the infimum. But we optimize over the set of sum of squares functions. And we simply minimize the integral where we multiply our what's it called, payoff function with the corresponding sum of squares density, and we still have our equality constraints fulfilled. We need that the corresponding measure is a probability measure. So just imagine that for one L in this set, this function is constantly 1, and this PL is equal to 1. And now what we can do is simply write that as a semi-definite program. But there's one catch. namely the following. The semi-definite program that we get might be infeasible even if the generalized moment problem that we consider has an optimal solution. And the reason for that is the following. So consider for any alpha the following constraint. So x to the alpha integrate with respect to mu over Rn is equal to 0. Well, there are probability measures that fulfill this condition. For example, the atomic Dirac delta at 0. But of course, there's no R such that a degree R SOS polynomial density function does. Right? So this is indeed a problem, but we have a workaround. So we will introduce a further relaxation in the following way. So consider a generalized moment problem like here, where we optimize over the set of probability functions and denote the optimal value of that generalized moment problem as B0. We have some assumptions on the set K, so it's a subset of Rn with non-empty interior, and each of these Ki are subsets of K that are closed. Then there's a result by Kuhn, Etienne de Klerk, and Postek, I think, which we can use. Namely, if you have a reference measure nu with known or efficiently computable moments, such that the moments are finite and have these and don't grow too quickly for some n greater 0, then basically this error here goes to 0 as R goes to infinity. What does that mean? It's basically if you fix an R, not an R, if you fix an epsilon, you can keep increasing R, and at some point you will find a feasible solution that is such that at most, so the strongest violation of any constraint or the optimal value is at most epsilon. Okay, and this epsilon can go to 0 or goes to 0 as R goes to infinity. So what does that mean for us? Consider the following example here, where we used again the some of the options of the Microsoft stock from '98. We again minimize and maximize with where we are looking for an option with strike price 105. And solving this analytically, we see, or we can verify that the optimal values are given by 5.125 and 3.375. And now doing it ourselves using semi-definite programming, we see that it is often, or that it's a good idea to first switch to an orthonormal basis to improve numerical stability. And what we do exactly will be to first define a orthonormal basis with respect to the reference measure that we use. And in this case, so if we use this reference measure right here, the corresponding orthonormal basis will be given by the Laguerre polynomials. They're defined like this. So the nice thing is they're available in closed form. And yeah, so as I just said, these form an orthonormal basis, meaning that if we evaluate this integral given here, this will be 1 if m is equal to n and will be 0 otherwise. And another thing that we will need is that this integral right here, where we do not start at 0 but start at k, is also available in closed form. Now, equipped with all these things, we can actually solve the problem, or yeah, so basically solve the problem numerically. What we do first is we normalize things. So we divide everything by the largest number that appeared there, which was 110. And now we maximize or minimize this integral right here, such that these inequality constraints are fulfilled. Right? This was the former right-hand side, which we want to be violated, or this equality constraint is supposed to be violated not stronger than epsilon r. And now let's have a look at the numerical results. First of all, these epsilon r's that I give here in the table are basically the smallest that you could choose, such that the resulting problem is still feasible. So if you solve the, for r equals 2, for example, if you solve this problem and try to make epsilon a little bit smaller, then the problem will be that you get an infeasible program. So you cannot, you don't get any solution anymore. And now, well, first of all, what you see is that, okay, the epsilon does really decrease. But if you look at the solutions for the upper and lower bounds, they do not seem to be that good, especially for very low values of r, right? So the lower bound, which we know is 3.375, is something like 5, is very close to the upper bound. And then only if you increase r for quite a few steps, you get something that is closer to the actual lower bound, but then the upper bound wasn't even computable anymore, because this is numerically rather unstable. So this was indeed a problem. And also you lose something, or what you do lose using that second relaxation is monotonicity, right? So these are not monotone bounds anymore when you do when you use the relaxation. And actually, if you use the relaxation, you cannot be 100% sure anymore that what you get is an inner range. So we use a relaxation for the inner range, which we relax again, and then we get something where we are not really sure anymore where this goes. So in the end, we get something that is quite close to the optimal range, but comparing that to the first approach that we took, we see that the first approach was a lot cleaner and gave better results. And well, this is also part of the conclusion now, that the outer range works much better than the inner range, and the outer range actually is often tight at the first level. And now future questions that one could ask is, what about the rate of convergence for the outer range? Can we say something about that, or are there any ways to well, study it? And another interesting question, at least for me, is can we find somehow a closed form solution for the bound B, which we can use to compactify the problem? But until now, I haven't been able to find one. Yes, so this is these are the references I used, and for some further reading, this is the well, this is a paper that's now available as a preprint of arXiv on arXiv, revisiting semi-definite programming approaches to options pricing, complexity, and computational perspectives. And now I'm happy to take any questions that are out there. Thanks a lot.
Thank you, Felix. So yeah, that's that. So I will first encourage the questions in the room, and people online who have questions, please turn on your camera so that we know that you are ready to ask a question. In the room. Yes, opinion.
Hi, Felix.
Hi, Kobe.
Asking a question.
Yeah, thank you a lot for your talk. I would like to ask 2 questions. The first question, I was just wondered about that there might be several fair prices. Is there a good reason why there should be many fair prices? This seems a bit kind of striking to me, I would say.
Really? So I would find it more striking that if there was only one price, because it's just like, okay, you have 2 other options, say, and then the idea is that, okay, this is not very restrictive, right? So it's only 2 prices that you have to kind of be in balance with to avoid arbitrage. So as soon as you're somewhere around here within that range you get, there will be no arbitrage possibilities.
Okay. And my thanks. And my second question, you add the constraints to be consistent with other price price options, right? But how are these price options determined? So for your example, for the Microsoft stock, for example, how did they determine?
Yeah, I see. Yeah. Yeah, that's a good question actually, because yes, as you said, we just assume that we have some other prices available. Well, I'm actually not sure how it's done in practice. So what we do is we simply assume if all other option prices are correctly priced, then we can add more to the existing set. But actually, what you do see in practice is that this no arbitrage assumption is violated by some option prices. So what is done is using different methods, for example, numerical methods like Monte Carlo or the Black and Scholes formula, to find bounds or to find option prices, and then sometimes these violate the consistency that we assume. So it's not strongly violated, just a little, I think. So yeah, but I'm not sure how it's exactly done in practice, so I can't answer that question.
Okay, cool. Thank you.
Do we have another question in the room? Yes, Bernard Morin, coming close.
Hello, Felix.
Hi.
I have a question. You said at some point that the first order relaxation is exact.
Yes.
Always.
Well, at least for the
cases where it's not.
For the cases where we tried, I'm not sure if it. So I'm not claiming that this is in general true, but for the ones that we tried, it was. At least for the outer range. For the inner range, of course not, as we saw in the thing. But
Yes.
with the with all the options that we try, or for examples that we tried, there are a few more in the archive paper. It was always tied at the first level. But this would also maybe be interesting to check analytically if this will always happen.
And maybe another question. So this problem is in 1D somehow, but you have several measures.
Yeah.
This,
the example.
The example you showed. What about several options, or several variables?
Yes. So in the example that I had, it was only one option, but you can also do that in multiple options. So multiple dimensions. So you have options that depend on multiple assets. That works. But then you don't. Then you kind of. Well, then you have a bigger space that you have to decompose. There are some figures in the archive paper where you see how you can do that, and depending on the payoff function. Yes.
And you still observe the exactness at the first order.
In the two decays, I think so. Yes. I'm not entirely sure. I would have to look it up, but I think yeah.
Okay. Thank you.
Yeah. Thanks for the question.
So I'm not seeing online questions. Are we seeing any other questions in the room?
May I ask a question?
Yes, of course.
Thanks for the nice lecture. So I'm not sure if I will now say it correctly, but is it correct that in the multivariate case, then you don't have the convergence because you don't have this parameter b? I mean, you have to find the b explicitly.
Exactly. So you can choose just some b, for example, and then solve the problem, and then increase it and see if the solution doesn't change much, by increasing the B, then this might be an indicator that the optimal solution is attained within the first one, but I'm not sure if you can be sure about that. So, well, then in the multidimensional case, you would maybe go back to kind of trial and error and try to find some nice values of T and M, of course, as well. You can also tweak on M. If you make that very small, of course, then the optimal solution has to be, if it's then still feasible, it has to be small with a smaller support. But yes, so there's no close formula for B. Yes.
Okay, okay. But in any way, you can just choose, as you say, a B and you solve, and you get a valid bound.
Yes, exactly. Yes.
That's already.
It might not be optimal, but
yeah, you get
yes.
a valid bound. Yeah, yeah.
Yes.
Okay. Thank you.
Okay.
All right, I think we came to the end of the question on Felix talk. Felix, thank you very much. It was a
Thanks for the opportunity.
session. And I guess that's yes, I guess we are clapping again for Felix and all the speakers of today.
Thank you.
And this is closing our first day of the workshop. Zoom tomorrow 9:30. Be there or be square. Have a good night. Bye to everybody online too. Have a good evening.
Thank you.